In this lecture, we're going to go over the isentropic efficiency of turbines. Isentropic efficiencies involve a comparison between the actual performance of a device and the performance that would be achieved under idealized circumstances for the same inlet state and, importantly, exit pressure. So if we have a turbine expansion process on an HS diagram, for state 2, what we're saying is we have a fixed pressure where we have the actual expansion at state 2 and the isentropic expansion at state 2s, which is at an expansion of constant entropy. Heat transfer between the turbine and the surroundings is ignored, as well as kinetic and potential energies. So with these assumptions, our mass and energy rate balances reduce at steady state to give the work developed per unit mass as our work is H1 minus H2. Since state 1 is fixed, H1 is known, so the value of work depends on the specific enthalpy at state 2. The work increases as H2 is reduced. So the maximum value for work for the turbine corresponds to the smallest allowed value for our specific enthalpy at the turbine exit. We can just figure that out using the second law. Since there is no heat transfer allowed, our entropy balance comes down to our entropy produced per unit mass is S2 minus S1, which again is greater than or equal to 0. Since entropy production cannot be negative, only states where S2 is greater than S1 are allowed for adiabatic expansion. The only states that can be attained adiabatically are those with S2 greater than S1. Since state 2S on our figure can be only obtained if there are no internal reversibilities, this is going to be our isentropic expansion. This is our state 2S. For a fixed exit pressure, the specific enthalpy at state 2 decreases as the specific entropy decreases. Therefore, our smallest allowed value of H2 corresponds to our state H2S, and our maximum work, so our isentropic work, is H1 minus H2S. So we define our efficiency of our turbine as our actual work over our isentropic work, or H1 minus H2 over H1 minus H2S. And so we're going to do two examples. We have steam entering a turbine at steady state with the conditions of P1 equals 1 bar, P1 equals 5 bar, T1 equals 320 degrees Celsius. Steam leaves the turbine at a pressure of 1 bar. We have no significant heat transfer between the turbine and its surroundings. Kinetic and potential energies changes are negligible. If our isentropic efficiency is 75%, we want to determine the work developed per unit mass flowing through the system. So we want to find our work per unit mass, which is equal to our turbine efficiency times our isentropic work, which is our isentropic efficiency times H1 minus H2S. From table A4, at 5 bar and 320 degrees Celsius, we have H1 and we have S1. So state 2, it's fixed by P2 equals 1 bar, and state S2S is equal to S1. So I'm actually fixing state S2S, not state 2 itself. So I'm going to go to table A4, and I'm going to look up 1 bar. And I'm going to look up my entropy. I want to get that my enthalpy is 2743.0 kilojoules per kilogram. So my actual work is 0.75, which is my efficiency, times my change in enthalpy, which is equal to 271.95 kilojoules per kilogram. So your actual work for your turbines is always less than the isentropic work. You can't get out as much power as you could if there were no irreversibilities present in the system. The next problem we're going to look at, we have water vapor at 10 megapascals and 600 degrees Celsius entering a turbine operating at steady state with a volumetric flow rate of 0.36 meters cubed per second, and it exits at 0.1 bar with a quality of 92%. Stray heat transfer and kinetic and potential energy effects are negligible. We want to determine the mass flow rate, the power developed by the turbine, the rate at which entropy is produced, and the isentropic efficiency of the turbine. So we'll start with the mass flow rate. So our mass flow rate is our volumetric flow rate divided by our specific volume. So we need our specific volume. So at 10 megapascals and 600 degrees Celsius, V1 is equal to 0.03837. I got that from table A4. So our mass flow rate is 0.36 meters cubed per second over 0.03837 meters cubed per kilogram, which is 9.38 kilograms per second. So next we need our power developed. Well, the work for our turbine is our mass flow rate times our change in enthalpy. So from table A4, I want to get my first entropy to be so state 2 we know is a two-phase mixture, so I want to go to table A3, and at 0.1 bar, I get HF and HG. I have H2, so HF plus my quality times, sorry, this isn't HG, this is HFG. So H2 so my work is equal to 9.38 kilograms per second times my change in enthalpy is 11.56 megawatts. Next, it wants the entropy produced. So our entropy produced is my mass flow rate times my change in specific entropy. I need my S1 and S2. So my entropy produced comes out to be 6.07 kilowatts per Kelvin. The last thing it wants is the isentropic efficiency, which is H1 minus H2 over H1 minus H2S. So I now need H2S. So S2S is equal to S1, which is two-phase. So I need a quality at state 2S. So X2S so my quality at state 2S is 0.834. So my new enthalpy is 2,187.5. So my isentropic efficiency comes out to be 85.7%. In our next lecture, we're going to go over the isentropic efficiency of nozzles.